who will speak about string-like amplitudes from surfaces. And yeah, please, Hugh, floor is yours.
Okay, thank you. Thank you very much, Misha, for the invitation to speak. It would be lovely to come to Moscow one day and speak in person, but this is certainly more convenient. Anyway, so it's nice to be here. I'm very happy. Misha was saying, this is traditionally is very informal. People will feel free to interrupt. I'm very happy with that. Please do interrupt. Please do ask questions. I won't necessarily be able to answer them, but I will try my best. So the sort of picture of what I'm talking about is the following. So we start off with a surface. Maybe this is better this way, right? Surface with boundary. And marked points. And I'll be a little more precise about that. Well, I guess to be more precise already, marked points. For today, I'm only going to have the marked points on the boundary. It's also possible to include marked points in the interior of the surface. Associated to that, there is a gentle algebra. I'm not going to assume that people know what that is, but I will explain it. Associated to that, there's an affine algebraic variety. And associated to that are the analogs of string tree amplitudes. And obtained by integrating over a region in the variety.
You just, I hope you will comment on gentle, on item 2 and item 4 and draw a picture of item 1.
Yeah, so I will. I mean, this is just to give people a very general sense of where the talk might be going. I should also say this is all joint work with Nima Arkani-Hamed, Hadleigh Frost, Pierre-Guy Plamondon, and Giulio Salvatori. So these my collaborators, other than Pierre-Guy, are physicists, and they are really motivated by the analog of string tree amplitudes end of the story, and so that's their interest in what they want to get to. While I am kind of motivated by that as well, I don't understand it very well. So my expertise is much more around the gentle algebras and close to the gentle algebras. So I will try to say something about the physics at the end. I don't mean that I'll try to say something about the physics, but I may not be able to fully satisfactorily answer all your questions about the physics. if you're excited about the physics end of it, there's lots of talks by Nima on YouTube. There are probably talks by Giulio on YouTube, or you could invite them to come and give a talk. Yeah. So there's a version. Well, so there's a version of this that was worked out by Koba and Nielsen in 1969 for the disk with n marked points on the boundary, from which they produce some non-crossing equations from which they get the string tree amplitudes. And so I'm going to begin by briefly discussing what Koba and Nielsen did. I'm then going to take quite a bit of time to talk about the same problem. So still thinking about the disk with marked points on the boundary, but from our more algebraic perspective. And then I'm going to say something about other surfaces. Okay, so let's begin with Koba and Nielsen. So we start with a disk with n marked points on the boundary. And we consider a set H of curves beginning and ending on the boundary, not at the marked points, and up to homotopy, preserving these conditions. So what that means is if we had a circle with, say, 4 marked points, we have this curve, which is equivalent to that curve. This curve is different. This curve is different. This curve is different. Let me just get that curve out of the way. And let me draw 2 other curves. Whoops. There's this curve and there's this curve. And those 6 curves are the full, every curve that, every legal curve, every curve is equivalent to one of these 6 curves. So there's, in general, if we have n marked points in the boundary, there are n choose 2 classes of curves. And I'm going to refer to them by numbering the points on the boundary from 1 to n. And then if I look at my disk, I can see that my endpoints of my curve are between I and I plus 1, and then between j and j plus 1. And I'm going to refer to that curve as uij. And just, I'm going to assume that I is less than j. And when I write things like j plus 1, of course, if j equals n, then j plus 1 is just 1, sort of the obvious things. So these are the curves. I don't, right. And this is going to be relevant somehow to physics because these correspond to You can ask about the momentum that's crossing one of these curves. Anyway, I'll say more about that soon. For now, we're just going to write down some equations. They're just some like random looking equations, and then we're going to try to solve them. So the random looking equations are as follows. For each curve in my collection H, I'm going to consider the equation UC plus the product overall D in my collection of UD to the number of intersections of C and D is 1. Where we decree that C intersects C. Where we decree that we draw the curves in such a way as to intersect minimally. So when we count intersections, we count minimal intersections. So in particular, two curves in the same equivalence class, I can draw them so they don't intersect at all. So the curve C, so if we pick a particular curve C, and we're looking at this equation that has UC as the first term, then UC doesn't appear in this term because while it is one of the guys in H, you can draw C so that its intersection with itself is 0. So the exponent that UC gets is 0. I'm going to write down actually a bunch of examples so it'll be hopefully super clear what.
So Hugh, is it true that the exponent is either 0 or 1?
Yes. So there are some things that I'm going to be saying where you could imagine other ways that I could say them, and I'm saying them these ways because we're heading towards a more general story, which I will, at least get to the beginnings of, where they will be exactly the same. So that on a more general surface, the point is on a more general surface, these intersection numbers will potentially be bigger than 1. But here, you're absolutely right. D intersect C is chosen minimally and equals 0 or 1. And well, as I'll write down in a moment, in a moment, I'll have to write down the combinatorial condition that characterizes when it's 0 and when it's 1.
So we can see from it that UYY is 0 for every I. UYY, where indices coincide. Because
I don't allow the indices to coincide, but the one that you're thinking of, I think, this is the next thing I was going to say. So let me say it, is if we look at this curve, so and this curve I would call I plus 1, this equals 0. Because the equation that corresponds to it is I plus 1 plus the product over PQ in the empty set of UPQ is 1. And this is an empty product, so it equals 1. So I plus 1 equals 0.
No,
is that where you were?
I think Sasha asked about curve which starts and ends on the same interval, so which is homotopy to the boundary.
Yeah, so I simply don't want those curves. Oh, I guess I didn't say that. Sorry.
You said that I is less than J.
Well, I did say I was less than J, but I mean, such a curve contracts to just a, so I guess I can say non-contractible. Such a curve that starts and ends at the same place will contract to just a point. And so we don't want those. They will, there's no, with a more, on a more complicated surface, there's no problem with having a curve that leaves between I and I plus 1, goes away, winds around somehow, and comes back to the same segment. That would be perfectly allowed. So I didn't want to. I wanted to say I wanted to exclude things in a more correct way. But yeah. So the UII plus ones have an equation associated to them, but the equation turns out just to be kind of trivial, and it just says that UII plus 1 equals 0. In the case for n equals 4, which is the first interesting case, there's we're just getting one other equation. Because if I have my curves 1, 3, and 2, 4, then the one non-trivial equation is u13 plus u24 equals 1. So we have a one-dimensional space of solutions for n equals 4. It's just a line segment. And the corresponding tree string amplitude is an integral over that line segment. T to the x, 1 minus t to the y, which is beta of x plus 1, y plus 1. This is Euler's beta function. And so here the t and the 1 minus t are simply playing the role of u13 and u24. So, and this is going to be the form of the tree string amplitude in general. It's going to be some integral. The arguments are going to be exponents, and the things we're going to be, oh, I guess I should write dt there. And the things that we're going to be taking the exponents of are the u's. So this is some kind of, so even for the disk, this is some kind of generalization of Euler's beta function. So now let's talk about what happens with general n. Well, notice that we have the same number of equations as variables. So you might expect that the answer is just going to be, you get some points, but that's not what happens. So what we get is an n minus 3 dimensional space of solutions. And in fact, if you have, the easy way to describe them is to take n points, z1, z2, zn, complex numbers, and then define uij to be a cross ratio zj plus 1 minus zi times zj minus zi plus 1 divided by zj plus 1 minus zi plus 1 times zj minus zi. And this is this solves the U equations. And I'll say why in just a moment. In fact, we can do even better than this, because we can say, if we say the z's are real and we fix 3 of them, so we can fix like z1 to be 0, z2, zn minus 1, we could fix to be 1, and zn we could fix to be infinity, or 2 if you'd rather, it doesn't matter. And if we assume they're real, then this parameterizes the real solutions. So you have n minus 3 variables that are left, and you can just do whatever you like with them, provided they have the right order, and you get each of the solutions for the U's. So why does this work? Well, it's a telescoping product. It's actually very easy. But I think it's.
Hugh, can you scroll up to the formula?
Sure.
This last Z, what is Z-I-N? I sort of.
Z, in here?
In numerator. No, in numerator.
Oh, I+1. Sorry.
Ah, it's I+1.
Yeah. It's just.
Sorry, Hugh.
Yes.
The equations look like equations of some embedding of moduli spaces of endpoints on CP1.
Yeah.
This is just the moduli space, yeah?
Yeah.
So n-3 dimensional.
Yeah. Yeah, I mean, this is a different. This is a partial compactification. If we focus on the U's, then they provide then the equations that I wrote down, what I called number 1, the equations for the U's define an affine algebraic variety, which is a certain partial compactification of the moduli of endpoints on the line. It's not compact. So it's not M0 n bar, but it has more points than just M0 n, but it doesn't have sort of all of what you would put in when you compactify.
Sorry for interrupting you again. Can you describe explicitly what boundaries do you add? So it's like the boundary read off from real case, like I mean, you don't allow 2 points which are far away to contract if the points in the middle don't contract.
Okay.
Is it what you're saying? I mean, so in real Grassmannian or like in real moduli space, right? If you contract point 1 and 3, and 2 is between them, then 2 necessarily should coincide with so that gives you some boundary, right? This gives you some compactification. So
right.
Is it the boundary that you add, or what? Or it's different?
I'm not sure how to describe it in terms of what we've added, though it's a perfectly reasonable question. But sorry, in this case, I think it's I think this does correspond to something that Falk and Goncharov have studied in this case. I think that's true. But I'm afraid I don't know how to describe what we're getting in sort of those terms.
No worries. Just was curious.
Yeah, no. I mean, it's a very good question. And it's sort of well, I mean, it bugs me that I don't have a better answer. I mean, it bugs us actually. We were talking, yesterday about the fact that it bugs us that we don't have a better answer. So anyway. Yeah. So let me just explain why these cross ratios do solve the U equations. Well, so it's easy to check that 2 implies that if you take a product of a bunch of uij's where say A is less than or equal to I is less than B, and C is less than or equal to J is less than D, you take that product of the uij's, then that is also a cross ratio. It's ZD minus ZA, ZC minus ZB, over ZD minus ZB, ZC minus ZA. And that's just a matter of that is just a telescoping product. You see the same factors appearing in numerators and denominators as you multiply them all together, and these are the 4 terms that don't get canceled out. And so then, if you look at the equations, the U equations that we began with, again, so just to write them down again, we have Uij plus, well, the product of UPQ, where PQ crosses IJ, but what that really amounts to is that I plus 1 is that P should be between I plus 1 and J, and oops, I want that to be strictly less than J. And J plus 1 should be less than or equal to Q less than I. So that those indices don't literally make sense, but you should interpret everything cyclically so that, you know, the P should be between I plus 1 and J, and then Q should be between J plus 1 and I, and maybe we have to swap the P and Q if need be. So that is the U equation says that this thing should equal 1, but this product, we can apply this telescoping formula to the product, and so we get well, the first term we just apply the solution that I wrote down. So the first term is Zj plus 1 minus Zi, Zj minus Zi plus 1 over Zj plus 1 minus Zi plus 1, Zj minus Zi. And the second term is the one that comes from the telescoping product and turns out to be Zi minus Zi plus 1, Zj plus 1 minus Zj over Zi minus Zj, Zj plus 1 minus Zi plus 1. And you notice that the denominators are the same up to a sign. And so you just add the numerators and you get 1. So that shows you that you did, in fact, get solutions. I guess it doesn't show you that you got all the solutions, but it shows you that you got solutions. So that you can then talk about integrating over the region where all the Uij are positive, integrating something of the form Uij to the Xij. And this is roughly the string tree amplitude. I'll rewrite this with a more specific measure in the next section. And I'll say a little bit more about what the nice properties of this are then as well. Okay. So I'm now going to switch gears and talk still about the disk with nmark points. But with this algebraic approach. So we're going to fix a triangulation of the surface, i.e. a subdivision into triangles by lines connecting, by diagonals connecting the marked points. Phooey, I thought I had got my picture all nice and drawn for me so that it would come back when I clicked, but no such luck. Oh well. So my picture is not very complicated. But so I'm just drawing a disk with marked points and a particular triangulation that is just going to be the triangulation that I'm going to be talking about. So there it is. And so associated so this triangulation I'm going to call T, associated T, there is a quiver. So quiver just means directed graph, but it's a warning that we're probably going to be starting to do representation theory. So the quiver has a vertex for every edge, for every diagonal of the triangulation. And an arrow between successive edges, between successive diagonals in each triangle going counterclockwise. So inside this triangle, we have 3 arrows like that going counterclockwise. Inside this triangle, because there isn't any vertex here, because it's not a diagonal, it's a boundary edge. We don't get to draw things to it, so we just get to draw one. We just get to draw one arrow inside of that triangle. And in the other triangles, since we just have one edge in them, we don't get to draw anything. So that's the quiver. A representation of a quiver is just an assignment of a finite dimensional vector space to each vertex and a linear map between them, between the corresponding vector spaces to each arrow. So, for example, we could take a subpath of the, so I want to take a subpath ignoring orientation, put a copy of C at each vertex, and the map 1, the identity map, between the corresponding C's and zeros elsewhere. That's an example of a representation. So my quiver, so this is the same quiver that we had coming from the triangulation, but let me just draw it there and just think about writing down a representation of this quiver. One way to do that is to pick some path through the quiver like that, and then just say, I'm going to put down a copy of C at the vertices that are on the path. I'm going to put down maps labeled 1 between them, and I'm going to put down zeros everywhere that's not on the path. I mean, that seems like a very specific choice of representation, but there's a reason that I want to sort of bring that up as a thing that I might do. In general, I could do lots of other things. I mean, I can have, the vector spaces don't need to be one-dimensional. I mean, if I'm just talking about representations of a quiver, I just put down any vector space, any linear map, that's a representation. There's something special about the representations that I just wrote down. And I want to get at that notion. In order to do that, I need to define one other idea, which is, which is also like a very simple idea. There is a notion of direct sum of representations in pretty much, the obvious way. If I had, we just take, so if I had the representation that was like this, if I had the representation like this, and I took its direct sum with the representation that was like this, that would be isomorphic to the representation that looks like this. Whoops, not like that. That would be isomorphic to the representation that looks like this. But where this map is the zero map, because when you take a direct sum, you just the linear map for each arrow is just the direct sum of the linear maps between the corresponding vector spaces, in each of the two things that you're taking the direct sum of. So in this example, this arrow was 0 and this arrow was 0, and the direct sum of 0 and 0 is 0. So we get this map. And the important point is that this guy is not isomorphic to him, because we can't just by changing basis turn this into that, because 0 doesn't turn into 1 by a change of basis. So you fairly easily convince yourself, if we say, so a representation is called indecomposable if it can't be written as a direct sum of non-zero representations. The representations that I described above in 3 are indecomposable. Now, typically, if we just took this quiver and we just asked about its representations, typically it will have many, many, many indecomposable representations. In some sense, unclassifiably many indecomposable representations. So if we just took the quiver as such, and we were just asking about the indecomposable representations, it's kind of a complete nightmare, and it isn't really talking to the surface. But it turns out that we can make the quiver talk much more to the surface in the following way. So we add some extra condition on the representations. So we say, consider
Sorry, Hugh.
Yes.
Do you allow multiple edges or loops in a quiver?
I don't disallow them. The quivers that come from a triangulation won't have, so the quivers that come from a triangulation won't have loops. The quivers that come from a triangulation, the disk, won't have loops or multiple edges. But in theory, I'm not excluding them. And what we're going to see is that when we pass to more complicated surfaces, we can definitely have multiple edges. And if we pass to surfaces that are a little more complicated still, more complicated than I'm going to even get to today, then we can also have loops. So such things can happen, but they aren't going to happen in the disk.
Okay, thanks.
Okay, so all right, so consider representations with the condition that the product or the composition of any two consecutive arrows in a triangle is 0. In this case, there are only finitely many, and they are exactly those. There are only finitely many indecomposables exactly those described by 3. Because what the quiver will in general look like is some triangles kind of stuck together. Oriented triangles stuck together. And the representations that I'm talking about, these sort of sub-path. Oh, I guess I didn't say this. Bother. I thought this. Sorry. Sorry. These are exactly the ones described by 3. If we impose an additional condition, which is what I meant for 3 to say, which is that 0 is elsewhere, and never going around 2 sides of a 3 cycle. So I need to put that condition in by hand here, but once I do that, then I have indecomposable representations that satisfy the relations. And once I impose those relations, these are the only indecomposable representations. So the indecomposable representations are really just the very most obvious representations that you could write down. It turns out that's all there is. Any representation that satisfies the relations is necessarily isomorphic to a direct sum of these representations, of these sort of obvious representations coming from just a path that doesn't wind around too much. Okay. So in the example that we were looking at, just to be super clear, in the example we were looking at, the indecomposable representations are those of the form that are either one-dimensional, so just put a C at some vertex. There are 4 of those. They're the ones that are two-dimensional. Put C at 2 adjacent vertices. There are 4 of those. And there's 2 other things you can do that aren't that. You could take this representation or the representation that's like this. So we have 10 in total. Now, what where I'm heading with this is that these representations, these indecomposable representations, of this quiver associated to the triangulation almost correspond to the UIJs. Sorry, before I go on to that, is the quiver and the representations, is it clear what I'm talking about? Are there questions?
I just have some mental block. So what's wrong about like taking a triangle, oriented triangle, put CCC?
Right. So nothing is wrong with that, but I just I mean,
it's also indecomposable, right?
Yeah, it's certainly indecomposable. I've just added this. I've just put this condition: the composition of any 2 consecutive arrows is 0. So I've just like told you not to do that.
Okay.
I mean, there's no a priori, there's no reason I had to do it, but I just told you not to do it. The point is that, so we'll see that imposing this condition gives us an algebra that is well, the technical term is gentle, but it gives us an algebra whose representation theory is easy to understand and is closely related to the geometry of the surface.
Yes. Sorry, my apologies. I just
I realize that this is probably this is more remote from the interests of maybe many of the people in the room or in the virtual in this virtual talk. And so I'm really I welcome questions, because if I would a bunch of the rest of what I'm going to say is really contingent on people having some sense of some degree of comfort with what I'm talking about here. So if there are questions, I really welcome questions.
Thanks.
Okay. Yeah, so the point is, this quiver, with some relations, we just get this very simple collection of indecomposables out. And my claim is they almost correspond to the UIJs. So that's now, I mean, in this example, we had n, the number of mark points was 7. So there are 21 UIJs. We only had 10 indecomposable representations. So there's a bit of a mismatch, and so I need to tell you something about how to fix that. One way to fix it is that, as we already mentioned, the equation for ui plus 1 is just that ui plus 1 equals 0. So we will happily forget about the ui plus 1s. So that's 7 of the 21 curves. That's 7 that we don't have to worry about. That gets us down to 14. So 10 and 14 is not so different. What I'm going to do now is actually explain how to turn a curve into a representation. So roughly the idea is as follows. So I have some triangulation, and I have some curve, and roughly what I want to do is to say, I'm just going to follow the curve, and I'm going to use that as, that's going to tell me about what sub-representation, or sorry, what representation I want to take. I have my arrows going backwards. So if my curve was, again, like that, then I would just take the sub-representation that is, that only sees the part, that only puts down copies of C at the part where the curve runs along. Basically what I'm saying is, if you have a curve, well, it crosses a bunch of edges of the triangulation. And roughly speaking, what we want to do is we want to take the curve, and we just want to say, put down a copy of C on the edges, crossed by the curve. And this explains the condition that Misha was wondering about, the condition that the composition, that you're not supposed to use multiple arrows in any given triangle, because if you have a curve crossing a triangle, well, it crosses a triangle like that, right? And so you just at most you most ever use one arrow in the triangle if you're trying to kind of mimic the behavior of a curve. The curve doesn't cross 3 sides of the triangle, so you can't ever have a composition. So that's sort of where this condition that the composition of any 2 arrows should be 0. Really, in this simple picture, one of the 3 vertices has to be 0, which forces the compositions to be 0. So this is not quite good enough, because if we think about this picture of this as a triangulation of the disk, like it's supposed to be, well, there was a marked point here, because this is a triangle. So there's a third marked point here. And so we could ask the question, what happens if I would have taken the curve that instead goes like this? This is also a perfectly good curve, but it's a different curve. From the point of view of Koba and Nielsen, it is a different curve because its left endpoint is now in this segment, not in that segment. So these two curves count as different, but they cross the triangulation in exactly the same way. So that's a problem. And the way we fix that problem is, well, so roughly the way we fix the problem is we say we have to sort of remove a little bit at the end. And the way that we remove a little bit at the end is going to sort of depend on the configuration at the end. And if you, and probably that's really good enough for having kind of a feeling about what the story is that I'm telling. I'm going to describe a bijection. I haven't quite told you what it's a bijection to, but I'm going to describe a bijection between curves and representations. And roughly it looks like this, except that there's a little bit of fiddling at the ends. To describe the fiddle precisely, the way it works is starting from the curve, remove the parts going clockwise around its anti-clockwise neighbor at each end. So in other words, if my curve was like this, then what I see is that this much of the curve is going clockwise around its anti-clockwise neighbor, which is here. So this much of the curve gets removed. Over on the other side, it isn't really going clockwise around its anti-clockwise neighbor at all. And so nothing gets removed. And so as a result, what we put down is just 2 copies of C for these 2 vertices. So that's the representation that corresponds to the curve. And if we would have instead
to say clockwise and anti-clockwise, you are these red curves oriented, or
no?
What does it mean clockwise and anti-clockwise?
Well, the surface is oriented. So
okay, yeah.
Yeah, so if we would have had the curve that started like this, and so this is the sort of worrying curve because these 2 curves have the same cross the triangulation in exactly the same way. When we come to removing things, again, at this side, we don't remove anything, but at this side, we see that we aren't going, we aren't going clockwise around the anti-clockwise neighbor. We're going, in fact, anti-clockwise around the clockwise neighbor. So you have to sort of, Anyway, so this guy, the way I want to think about it is that either it's going this way or it's going that way, and you see that this guy is already going this way. So we don't remove anything here. As a result, we write down the representation that includes this vertex. And I mean, I should have been clear. I don't get to choose what vertices exist. There's always the same vertices. There's always the same quiver. I didn't draw the quiver because it just gets things cluttered. But so we always have the same 4 vertices. We're always representing the same quiver. But what we get to choose is which vertices am I going to put down a copy of C at? Which ones am I not? And this is how we do it, starting from the curve. Now, there's one funny thing that can happen, and this is just sort of this is kind of a technical point. It's not not so important just for having a feeling for what's going on. Let's see what happens if we start with this curve. Well, so we see that it is going clockwise around its anti-clockwise neighbor from this end like that. And it's going clockwise around its anti-clockwise neighbor from this end like that. And so the whole thing disappears. There is one way for this to happen. For each diagonal. So for each diagonal, you can draw exactly one curve that will just totally disappear, and it sort of disappears from one end and it disappears from the other end, and the two ends meet at this particular diagonal. And so there's one way to do it for this diagonal, there's one way to do it for each of the diagonals. So it's a theorem of Assam, Brustle, Charbonneau-Jodoin, and Plamondon, that I mean, maybe it may even go back earlier than them, because this their statement is more general. It deals with any unpunctured surface. But so there is a bijection from the set H of curves minus the short curves that I said we didn't mind, the removing these I plus 1 curves, to the indecomposable representations of Q with the relations specified that you can't go around the two sides of a triangle, together with this set of just funny objects that, you know, I won't get into why they're called this, but they're called PI shift. Anyway, these objects for I in the set of diagonals. So we have some extra objects that correspond to the diagonals, but basically we just have a correspondence between curves and representations. And I'm going to notate it by saying that the ij curve corresponds to a module mij, and mij could be one of these like funny phony modules that isn't actually a module. So I mean, this may, I don't know. I hope I've been going for a while, and you know, this may seem, you know, we are in some sense, it's going to get better from here, I think. It doesn't. So what we're going to see is that out of this module, we can get back to some combinatorics, and that's what I'm going to explain now. And it would have been possible, in fact, to just go directly from the curve to the combinatorics, but I feel like it would have been totally opaque what was going on. So that's why I did want to go via the algebra, which is, I mean, also it's what I like, it's what I do, but I also think that it you know, provides some kind of like explanation of what is the story that's at work. So thus the algebra, but we're sort of now heading, you know, we've gotten as far into the algebra as we're really going to get. We're heading back out now. So how do we, given some algebraic objects, how could we extract some combinatorics? And in particular, the goal is going to be solving these U equations using somehow these modules, these coming from the algebra. So let's number the vertices of Q, 1, 2, up to n minus 3, arbitrarily. I don't care how you number them, but just number them. And now associated to a representation of Q is a dimension vector, which is just the n minus 3 tuple of the dimensions at each vertex. So this is just, and this is just denoted dim. Yeah. And so for the representations that we've been talking about, this tuple will just have zeros and ones in it. In general, it could have things that are bigger. And let's introduce variables y1 to yn minus 3, and let me write y to the power of the dimension for y1 to the dimension of the vector space at vertex 1, y2 to the dimension of the vector space at vertex 2, and so forth. So so the dimension vectors get encoded as monomials in these variables. A subrepresentation of a representation is just a vector subspace at each vertex with the property that the image under the arrows of the subspace lies in the subspace at the corresponding vertex. So in other words, let's just look again at an example. So if we had the representation of our quiver, which was like this, what are the sub-representations of this quiver? Well, I would be allowed to take just the first vertex, and I'm not going to write down the arrows because there's no. Well, I actually already didn't. But let me put them in there to begin with. But for the sub-representations, I'm not going to even write the arrows. I'm just going to write the dimension vectors. So I could take just the subspace that is, I could take the subspace that is the whole vector space here and is zero everywhere else. And that's perfectly fine. And I could do the same thing with the vector space over on the right, and that's perfectly fine. But I would not be allowed to take this guy. He is not allowed because I've selected the whole subspace at this vertex. But that means that I have to also select select the image of this guy inside here, which is all of this guy. And I need to select his image inside here, which is all of this guy. So if I want to have the middle vertex, then I must have the two end vertices as well. I can also have nobody, of course. And there's one other subrepresentation that I can have. I can have the subrepresentation that looks like this. that's also perfectly fine. It's not indecomposable. So these three are indecomposable. This guy is not indecomposable, but that's fine. I never said my subrepresentation should be indecomposable. So I get a subrepresentation. So I can list off the subrepresentations, and this is not hard, right? This is for representations like this, which are just formed by taking some path through the quiver and putting down some single one-dimensional vector spaces. This is not hard. This is really just a combinatorial thing. If you want, you can really think about this path. The arrows in this path as defining a poset structure, and what you're really doing is you're taking an order ideal in that poset. Now we can define what's called the F polynomial. Is just the sum over all the submodules of y to the dimension of the submodule. So if I number my vertices here, 1, 2, 3, 4, then in the example that I was just looking at, we would have Fm equals y1 plus y3 plus y1, y2, y3 plus 1 for the 0 representation plus y1, y3. Okay, so right, so each of these subrepresentations gave rise to one of the terms in the F polynomial. So, and we'll just define for the funny guys, these funny PI shifted guys, whatever they are, we'll just say they don't have any F polynomial. And we'll also say that they don't have any dimension either. PI shifted by one, its dimension is just 0, is just the 0 vector. So now we can state an algebraic way to solve the U equations. So we set Uij to be equal to 1 minus y to the dimension of mij. So this is a monomial in the y's, divided by the F polynomial of mij times the F polynomial of mi plus 1, j plus 1. And so this gives us an expression for the Uij's in terms of the y's, which are n-3 variables, which is the right number, since we want something that's n-3 dimensional in the end. We get some parameterization of the solutions in this way. The proof of this depends on the fact that you can rewrite the U equations in more representation theoretic terms. You can say what it well, in this case it's all very simple, because I mean the exponents in the U equations are just zeros or ones, but more generally the point is that those exponents are really something that has a representation theoretic meaning, and you can again make a kind of telescoping product, but over the what's called the Auslander-Ruyten quiver of the algebra. So there's some other scaffolding that allows you to do a telescoping product and again prove that these things do solve the U equations. this allows us to write down the integral. So it's going to be the integral over where all the uij's are non-negative, uij to the xij, dy1 over y1, dy n minus 3 over y n minus 3. So this is, and somehow the fact that we're, well, so it turns out it's just convenient that it's convenient the way that, you know, once we parameterize in terms of these y's, then the measure that we have to take can just be written down very easily like this. So this defines an integral for any n, and it has some interesting properties. And this is you know, sort of maximally far away from what I know much about, but
sorry, Hugh.
Yeah.
In the formula for uij, there is a single y, no indices.
Yeah, sorry. Did I not? Yeah, I think I explained. I'm writing y to a dim to mean y1 to the dimension at vector space 1, y2 to the dimension of vector space 2.
I see.
So yeah, so that's what was meant there. So this is really a monomial, and these are polynomials in the same set of variables. And
sorry, I missed it. What are xij? Just any collection of parameters, or?
They're the Mandelstam variables. So they're thought of as, so they're the squares of the momenta. You know, it's yeah.
Well, we can treat them as external parameters, right?
Yeah. That's the idea. That's the idea. They're external parameters.
Well, may I interrupt? So hi.
Sure, hi.
So it's actually so there are momenta related to each particle, so to speak. So as far as I remember from my childhood years, and xij are scalar products of those.
Yeah, exactly.
And in fact, in order to satisfy the projection invariance, say this, actually the square of each momentum must be -1. This is called tachyon condition in string amplitudes.
I don't.
So they are in principle, they are not, they are vectors, say, in some d-dimensional space, like 26 dimensions or whatever. So it's,
yeah.
But from the point of view of amplitude, they're just numbers, so nothing more than numbers.
Yeah. Yeah. And so the interesting thing about, or one of the interesting things about the integral, and which, you know, connects it to the sort of behavior that you want for string theory, is that if xij equals 0, then the integral factorizes as a product of two integrals. Product of two such integrals, you cut the surface along the ij curve, and then contract the curve to a mark point.
You mean in the case of disk?
Yeah. I mean, everything really, I've so far been talking about the case of a disk, but the goal is that this same kind of thing should happen. I mean, the plan is that the same kind of thing should happen for any surface. That's what we're aiming for.
And then this contraction is sort of Deligne-Mumford compactification, or what?
Well, I mean, I don't think I need to say Deligne-Mumford compactification or anything. I mean, I'm just saying, I mean,
well, you choose so if surface is more general, so you just draw a loop on the surface and contract it to a point, right?
Yeah.
Okay.
Yeah. I mean, well, so this right now, what I'm doing, it's interesting, but it's harder to say what happens if you draw a closed curve on the surface. But if you draw a curve like this on the surface, where the kinds of curves that we've been talking about all along, which a curve with two endpoints on the boundary, then it's very clear what you mean to say cut along the curve and then contract to a marked point. And in this case, so this is saying that the integral for this 5-point guy turns into the product of an integral for 4 points and an integral for 3 points.
Mm-hmm. Are there any recurrence relations which connect different Xij?
The Xijs are just they're independent of each other.
Well, I mean, some dependence. Well, I don't know. Just assume that Xij are some integers, right? So, and you write some generating functions with respect to these Xijs. Well, do you have some relation between these integrals for different Xijs?
Maybe. I don't know.
Mm-hmm.
So that's what I wanted to say about the disk. And so finally, I want to say a little bit about what happened. So finally, I get to the sort of new stuff, which is what happens with other surfaces. So let's say we're dealing with a surface with boundary, marked points on the boundary, at least one on each component. So again, we can define H to be curves with endpoints on boundary, not at marked points, up to homotopy that preserves those properties. And things work much the same way. We can again write down for C in H, we can write down this equation, UC plus the product over D in H, U D to the number of intersections of C and D, and require that it's 1. And this is now sort of more exciting because it's not just the number of intersections is needn't be 0 or 1 now. It could be more. If you just try to sort of go at this with your bare hands, then it might be difficult. There's actually two. So and the physicists after Koba and Nielsen had done this thing with a disk, people were conscious of the fact that one should think about more complicated surfaces. This is sort of a very natural thing to do. Sort of after you expect the sort of tree level approximation to be associated to the disk, and then you expect the higher loop corrections to be associated to surfaces of higher genus. So the physicists want to understand what's going on for these higher loop corrections associated to other surfaces. But in 1969, people couldn't figure out how to do that. And it seems like the technology, some of the technology that we've been able to bring to bear helps. So let me just sort of quickly say how the whole story, the representations still work much the same way. So that, for example, let's consider an annulus. We could pick a triangulation like this. I could, if I might have a curve on my surface, which could be something, for example, looking like that. What we notice is that this curve crosses this edge of the triangulation more than once. And so what that's going to mean is that, I guess I'm getting ahead of myself. There's all kinds of things that are happening in this picture that are not exactly like what we saw previously. If we try to, first of all, we could try to figure out what is the quiver associated to this. Well, so that quiver is going to have two vertices, one vertex for this edge and one vertex for this edge. And it's going to have two arrows, one for each of the triangles. So there's a triangle, this sort of inner triangle where there's this arrow. And then if you look at the outer triangle, what you see is that there's another arrow, which I'm just going to draw. Oops, I'm going to draw. So there's another arrow, which goes like that. So in fact, the quiver looks like two vertices with two arrows. And what we see when we try to think about this curve, if we try to tell the story that we told before, everything just works. We look at the curve, we don't have to remove anything. I chose it carefully so we wouldn't have to worry about removing things, so we don't have to remove anything. So to figure out what's happening, well, we just walk along the curve and we see that we have an arrow. We put down a copy of C at vertex 1, and then we get to vertex 2, and then sorry, I have my arrows all backwards from where I'm supposed to. And it will just confuse me if I don't fix them. So we put down a copy of C there, and then we have an arrow, and we're back at vertex 1 again. And this is, so we have the two arrows alpha and beta, and this is arrow alpha, and this is arrow beta. So, from the curve, we kind of clearly get to this information. We have a sort of walk through the quiver that's going along specific arrows. And the point is that we can turn this into a quiver representation just by saying, well, what is this telling us to do? This is telling us to put two copies of C at vertex 1 and one copy of C at vertex 2. And for the first copy of C at vertex 1, is going to be the image of the map along the first arrow alpha, and the second copy is going to be the image of the map along the second arrow. So the point is the combinatorics of curves and representations just works equally well in this setting. And this is actually also part of the result that I cited from Assam, Brusle, Charbonneau-Jodoin, and Plamondon, that you just, again, get this dictionary between representations and curves. And so this, again, allows you to write down the same solution as before. This solution 4 that I had still solves these new U equations. And that's not quite all the story that we need for the representation, for the physics, because we also want to consider a set of closed curves. And for C, a closed curve, we want to write down the equation that UC plus the product over D in our usual H, not the closed curves. UD intersection of D and C is supposed to be 1. So this is super easy because we already supposing that we already understand how to solve the for the U's that come from H. This just, the solution to this is just to say that UC equals 1 minus the product of D in H of UD to the power D intersect C. So this is, I mean, there's nothing to solving it, but the point is that the region we want to integrate over is where UC is non-negative for C in H union H super C. So in other words, we have conditions that come from both the open curves that we were mostly talking about and the closed curves. They all give us conditions on the domain that we're supposed to integrate over. And the idea is that then this is supposed to, a similar integral should be the analog of the string tree amplitude. There's more work for us to do in actually figuring out, how to do that. The case that is more worked out is one that is where you have a disk with a single puncture. That's also possible to do. It creates some extra complications that I don't want to talk about, though, because now you also have to deal with curves that spiral into the puncture. So you get another, there's another kind of behavior that you can have once you have punctures on the surface. But so that's anyway. I think I've run out of things to say, so I should stop now. Thank you.
Yeah, thanks, Hugh. Questions? More questions? If you just take a puncture with, disk with puncture with free boundary points, will you get D? So some kind of, is your construction related to some D4?
Yeah, not as closely as you might think. So the algebraists, so people who do cluster algebras, if they are going to do so if they were going to look at this triangulation, would typically, so you'd write down the quiver as before, and so the quiver is just going to be so it's just a cycle. Oh, so I guess this would actually be D3, which would be A3. If you were a cluster algebraist, this is D3. But if you were going to do cluster algebras, you would so you think about this quiver with potential. So this is a way to find the relations, a way to impose some relations on the quiver. And for cluster algebraists, you take a quiver with potential, which includes a term for the puncture. So you take the product of the arrows around the puncture and you put that in the potential. And that means that these three arrows, all for cluster algebraists, these three arrows would also satisfy a relation. So these three arrows satisfy the relation that the composition of any two of them is 0. We don't add this term to the potential. So we have more. So we simply don't impose that relation, and and so we just have a 3 cycle without any relation, but that has some disadvantages. It's an infinite dimensional algebra. You can just go around that cycle as long as you want, and it's a perfectly good. Those are perfectly good elements in that path algebra. So this path algebra. So it's infinite dimensional, but it seems to be the right gadget. Well, it is certainly the right gadget to describe what's going on the surface in the simplest way. Because the simplest thing to say on the surface is, if I have my 3 points and a puncture, I might very reasonably ask about a curve that does that. And if you're a cluster algebraist, then you'd say, oh, well, that curve has self-intersections. We don't want that curve. But that doesn't seem to be the logic at play here. We were actually pretty confused by that because, I certainly spent a lot of time staring at cluster algebras. And so I was assuming that, cluster algebras must be telling us the right thing to do. And that really didn't seem to be the case.
So you don't have this skin relation or anything like that? You don't know how to resolve self-crossings?
Well, we simply don't have. We're not in the cluster algebra. So, we are. It's not that I think it's not that there aren't relations. I mean, but it's simply that if you just sort of take the approach of suppressing everything from the start that has self-intersections, then you sort of miss what's going on. You should think about them. They're present with their self-intersections, but yes, they have relations that, you know, relate them to the guys without self-intersections. So it's not that they, but somehow you get the wrong picture if you just try to suppress them from the beginning. I don't know if that, I hope that maybe made a little bit of sense. So the point is, I want to have them in the story, even if in the end, I want to be able to say, oh, well, they're related to the guys that don't have self-intersections. And in order to have them in the story, the most natural way to do that, representation theoretically, is not to impose a relation. So which means that now I can have curves that just like wind around the puncture as long as I want, and they're perfectly good. They're perfectly good curves, and they correspond to perfectly good representations of this algebra.
Well, okay.
I have a similar question, cluster question. So, as long as I understand, your solutions to your equations involves the information about the given triangulation. Is that correct?
Yeah. So it's.
So how the parameterization changes if you change the triangulation?
Yeah, that's a great question. We haven't looked into that carefully, and that's a great question. Yeah.
It just historical remarks that, of course, it was in the core of Veneziano amplitude, this changing of triangulation and changing these flips. So because it was actually the defining property that the answer will not depend on how we split it into triangles.
The answer, you mean the integral itself? Or?
Yes, the integral itself.
Yeah, but maybe expression for the integral will be kind of much simpler for one triangulation, and now it's all the same.
Not.
Well, I mean, for a disk, you know, maybe you prefer the triangulation where everybody is connected to one point, right? I mean, that's sort of maybe that's a little bit. Maybe the combinatorics is maybe a little bit more straightforward to work with, but.
One more question. The representation theory of Quiver is rather well studied.
Mm-hmm.
Whether the knowledge that our Quiver is set, a plain Quiver, helps in analyzing these representations.
So the feature of the Quiver that is really helpful is the Quiver are what are called gentle, or with punctures locally gentle, but let me just stick to gentle. So what that says is that locally at any vertex, because it's coming from triangulation, locally at any vertex, it basically looks like this, where there's at most 2 arrows in, at most 2 arrows out, starting from any arrow, there. Sorry, how do I want to say this? There are relations that there are 0 relations, which mean that. Starting from alpha, there is at most 1 beta with beta alpha non-zero, and at most 1 beta with beta alpha equals 0. So that's what's That's what these dots are intended to represent relations. So this composition is 0. This composition is 0. This composition is not 0. This composition is not 0. So so they look like this, or you can erase some arrows, and what you get once you erase some arrows is also fine, but you can't add arrows. So that's sort of the local structure. Gentle algebras were introduced by Assam and Skovronski in the 80s. So and so the fact that the representations, that the indecomposable representations have this combinatorial description, basically goes back to Butler-Ringel. Well, so they give a combinatorial description of the indecomposables. Their description is not yet really in terms of surfaces. The connection to surfaces is something that's come up in the past 6 or 7 years as a result partly of work of Haydn, Kaczorkov, Kontsevich, who show that there's some deep connection between gentle algebras and Fukaya categories of surfaces. But then also people working in gentle algebras were inspired by that and sort of also thought about, connections between gentle algebras and surfaces. And so there's a lot to say about, well, there's a lot to say about gentle algebras and surfaces. Anyway, maybe I've said more than enough at this point. Sorry.
Sorry for naive question. Is it true that you can realize this gentle algebra as kind of Quiver for triangulation of some surface?
Yeah.
So any gentle algebra, for any gentle algebra, you can draw a surface, draw a triangulation, and draw the corresponding quiver, and you will get this quiver like that.
Yes.
Okay.
But
the surface can be complicated, right? So
the surface could be complicated. Yes. Is there anything else I need to? No. So yeah, the surface could be complicated. But yes, any gentle algebra comes from a surface. So this is work of Pierre-Guy Plamondon and his collaborators that really have this. There's really a dictionary. You may need to include sorry, you don't need to include. So punctures precisely cause a problem because punctures correspond to algebras that are not finite dimensional. And it turns out that we need them, but those are what are called locally gentle algebras. But yeah, so I think for gentle algebras, it is simply true. Corresponding to an arbitrary gentle algebra is a surface with a dissection of the surface. So there's some additional, it's somehow special that the gentle algebras that we're dealing with there's some, so for more general gentle algebras, you have to decorate the surface with some, you have to decorate the surface in some way. So, yeah, sorry. I mean, I could, well, anyway, there's some, I mean, so yeah, so it's not just it's like a surface with a, so it's like a surface with a triangulation, but it's a little bit more general. So instead of just being a triangulation, you're allowed to have polygons that are larger than triangles, or in fact smaller than triangles. So you just have a dissection. That's the more general statement. gentle algebras really correspond to these surfaces with dissections, not necessarily surfaces with triangulations.
Okay, and for more general surface, probably not from the disk. So is it because for disk it seems like to be true that if you take like reducible representations, indecomposable representations that you described, and kind of take some dual space, assign to each indecomposable representation a number. Then you sort of describe like local system on, well, kind of flat connection on this disk with a one-dimensional fiber. Is it true for more general surface that one can sort of parameterize flat connections just by considering decomposables?
Well, is that right though? I mean, that seems like I would have thought that would be too much information for is that the right amount of information for the disk?
Well, basically like maybe it's too much because you have for fast connections you have relations, right? So if you have Sorry. Oh, okay. Mm-hmm. Yeah. More questions? Well, it's probably too late now. Thanks, Hugh.
Oh, it was a pleasure.
Yeah. Can you send your notes?
Yeah, sure.
Also.
Sure.
Okay. Thanks a lot.
Oh.